tutorial, I will explain the basic concepts of the chemical machine paradigm. This paradigm is a method for concurrent programming that is quite different from other approaches and not very well known. This method does not use threads explicitly or any representation of explicit starting of new processes or new threads. Instead, it is adopting a declarative approach where you just say that certain computations must be concurrent and parallel, and computations will be scheduled by the runtime engine automatically. The chemical machine paradigm is based on a chemical metaphor, or rather, it is just inspired by it, and the chemical metaphor is the easiest way, in my opinion, to learn how to use the chemical machine paradigm. This chemical machine method is based on a single principle, which is that concurrent computations should be able to find their inputs automatically and start automatically. Once you understand this principle, you will be able to write concurrent programs by systematic and logical derivation of the code in the chemical machine rather than by guessing and debugging. To begin, let us imagine that we have chemical substances that are dissolved in a large tank of water, say. In this chemical soup, so to speak, there will be different chemical reactions because molecules will randomly come together and react. The basic process is that you have some molecules that can react and produce other molecules as a result. The reaction proceeds by first consuming these two molecules. These are the input molecules of the reaction, and then producing the two output molecules of the reaction. Now we are going to consider completely arbitrary and virtual abstract chemistry rather than try to simulate actual chemical reactions. The chemical machine paradigm is not a way of simulating actual chemistry. It is not at all related to chemistry as a science. It's just inspired by the idea that concurrent processes should start automatically and in parallel, just as chemical reactions start automatically and in parallel between all kinds of molecules, as long as you put the molecules together. So, because the molecules are going to be completely arbitrary and abstract, we can postulate any kind of molecules and any kind of reactions between them. So, for example, we could postulate that there exists molecule A, molecule B, and molecule C, and that these two reactions are possible between them. This is up to the programmer. Note that these reactions are nothing like something that could actually occur in real life, because the molecules A and B disappear and the molecule A is emitted after that. This cannot happen in real life. Or that molecules A and C are consumed, they disappear, and nothing is emitted. No new molecules are produced. But we're going to use these molecules and reactions in a virtual simulation, and so the simulator can certainly support these reactions. It's just going to simulate that A and B disappear and then A appears. So this is how we could visualize these reactions. The molecules A and B come together, they disappear, and then the molecule A appears. Or molecules A and C come together, then they disappear, and then nothing more is created. So let's imagine that we implemented a simulator for such behavior, and we allow the programmer to define arbitrary molecules, arbitrary reactions between them, and to specify what are the initial molecules that are present at the reaction site, so to speak. And then the simulator will just look over all the possible reactions and try to execute them until repeatedly. So try to find more and more possible molecules that could react with each other until no more molecules can react. So that is the job of the runtime simulator or runtime engine of the chemical machine. Now, certainly this is possible to implement. So assume that we implement this. How can we use this for actual useful computation? Well, here's how. We make just a few adjustments to this picture, and the main adjustment is that each molecule now is required to carry a value. Not just a molecule A, but a molecule A with, say, value 5. It's just imagine a value that is carried on top of a molecule. And that value is going to be just a value in our programming language. So we're going to embed this chemical machine into some programming language. I will be using Scala with the library called Chymyst that I implemented. But this can be done with pretty much any programming language. And there are implementations for Haskell, OCaml, and other programming languages. So once we impose the requirement that each molecule carries a value, then we cannot just write a reaction A plus B goes to A. We need to specify values for each molecule. That means, for example, we can write like this. Instead of the chemical notation A plus B goes to A, we would write A with X plus B with Y is going to A with Z, where X, Y, and Z are going to be some values now. Clearly, the reaction needs to be able to compute the new value Z, and the natural way of doing that is to say that a reaction also carries a function that computes Z out of X and Y. X and Y are naturally going to be given input values for the reaction, and the reaction can have a function that computes new values out of the input values and put the new values onto the new molecules that it emits as the output molecules. So this is still pseudocode. Another example would be this, where two molecules are consumed by the reaction. No new molecules are emitted, but the body of the reaction, which is that expression that we now have to write, can execute a side effect and print some value that is computed out of the values that were carried by the input molecules. So in this way, we now have enriched the molecules with values and reactions with functions. And naturally, reactions become functions of the input molecules' values. Let's visualize how that works. For example, like this. Molecule A carrying a value X and molecule B carrying a value Y react. They both disappear. Then the reaction body, which is this function, is going to be run and executed, run on some thread by the runtime automatically. The new value is computed, the Z, using some expression, and then a new molecule A is emitted with the value Z. And in this reaction, the two molecules come together to the reaction site, which is just a virtual place where they go and wait for each other. Then they both disappear. Then the reaction body is evaluated, x plus y is computed, the side effect is performed, and that's it. Nothing else needs to be done. No new molecules are to be emitted. So the programmer can define such reactions. The programmer defines what molecules exist, what are the types of data that they carry, and what are the functions that each reaction carries, and what are the possible reactions. The syntax of the Chymyst library in Scala that realizes these definitions is summarized in this example. It is the syntax that's just a little more verbose than the chemical notation pseudocode that we have just seen. First, we need to declare the molecules. This is how it is done. We use this method m that declares the molecule, and we need to specify the type of the value that the molecule will carry. Then we can define a reaction. Reactions are defined using this go method, and the syntax is that of a partial function. So reaction can specify that these are the input molecules. The plus is just the chemical notation plus, which is just a separator. X and y become pattern variables that can be pattern matched as standard in Scala. And then we write some expression. This expression can be arbitrary Scala code depending on the input values of the input molecules. And we can also emit a molecule. So the syntax for emitting the molecule is just this, and the syntax for consuming a molecule is the same, except that it needs to be at the left-hand side of a case expression. Finally, having defined a reaction, we need to declare a reaction site, which is done using the site method. The arguments of the site method are all the reactions that we have defined at this reaction site. Later we will see more examples where there are multiple reactions. So the basic concepts of the chemical machine are just these. There's nothing else in principle that we need to learn about. Now we can reason logically in order to find what kind of molecules and reactions we need in order to implement some specific concurrent program. Programming in the chemical machine is the question of what molecules and what reactions do I need to define in order to model a certain concurrent logic. In this way, concurrent programming in the chemical machine is very declarative. It does not tell the chemical machine when to run reactions, how many of them to run, and so on. It doesn't tell that directly. It doesn't use any commands to run a reaction now or something like that. It just declares certain molecules and reactions, and then we can emit initial molecules, and the runtime of the chemical machine will run everything that we have defined, repeatedly finding molecules that can react with each other, computing the new values, putting the new molecules back into the reaction site, again finding new molecules, and so on. Our first example is an asynchronous counter. The task at hand is to simulate a counter that has an integer value, and the counter needs to be incremented or decremented by non-blocking requests. And it should be safe to do that from different processes running in parallel. In order to implement this functionality, we need to decide which molecules we need to use and which reactions they should have. Nothing else needs to be written, no other code. So how do we do that? Let's think about the values that we are required to manipulate. So there's this counter with an integer value, and we should be able to manipulate it concurrently. The only way to do that in the chemical machine is by putting this value on a molecule. So clearly we need a molecule that will carry this integer value. Let us define that molecule. To increment and to decrement means to request something concurrently. But the only way to request or to signal anything in the chemical machine is to emit a molecule. The chemical machine has only two primitive notions, molecule and reaction. There's nothing else. There are no flags, there are no special values or global mutable state that you can manipulate to tell the chemical machine to do something. The only thing you can do is to declare molecules and reactions. So therefore, the increment and the decrement signals must be modeled by emitting certain molecules. So we need a molecule for increment and a molecule for decrement. Now these molecules don't need to carry any values because it's just a signal. I want to increment the counter by 1. I don't need to put a value. So let's define them with unit values. Unit is just as good as a value. Now we have 3 molecules. Let's think about how they will work. Well, clearly we need a reaction that will consume some of these molecules. What if a reaction consumes the increment molecule? How can it also manipulate the value of the counter molecule? It cannot unless it also consumes the counter molecule. The only way to manipulate something in a reaction is to have that something as the input value. Therefore, this reaction must have the counter molecule and the increment molecule both as input molecules. So that's how we can write that reaction. We pattern match on the unit value like this, and on the integer value of the counter like this. This reaction will consume these 2 molecules, and then we need to increment the counter, so we compute the new value of the counter, put that value on the counter molecule, and emit that molecule. So that is done using this very concise code. This is emitting the molecule counter with the value n+1. And similarly, the decrement reaction will do the same thing. Here's how we can visualize these reactions. Now, let's notice that we still need to emit these reactions, these molecules before any reactions can start. How shall we do that? Well, the only thing we should decide is how many to emit initially. Well, clearly we need to emit 1 counter molecule. So let's do that with some initial value. Doesn't matter what value for now. Could be some reasonable initial value. Then let's emit some more molecules, increment and decrement. Now this syntax is just equivalent to emitting several molecules, one after another. So we can visualize what happens when we emit these molecules. So first we emit counter, then we emit a bunch of increment and decrement molecules. Counter can react with increment, or it can react with decrement. The chemical machine will decide in some way, non-deterministically, which reaction will start if all of these molecules are available. So after these operations, which are very quick, these are non-blocking operations that don't wait for any reactions to start or to finish. So these are very quick operations to emit molecules into the reaction site. And after these operations, the reaction site will contain a counter and an increment and a decrement, say. And let's suppose that first it reacts with the increment. Then both of these molecules will be consumed, they will disappear, and then the new molecule with the value 101 will be emitted into this reaction site. Then it can react with the decrement. There are no more increments. We have emitted just 3 more decrements. So it will react with each of them one by one, because there's only one counter molecule, so it can only react with one decrement molecule at a time. And so, one by one, they will emit new counter molecules, and eventually you will have this counter molecule with value 98. That will be the result of running this program after some time. Notice that this is completely safe. There cannot be a race condition in the sense that while one of these reactions is computing the n+1, there is no counter molecule present at the reaction site. And so nothing can start this reaction that could decrement the value while it is incremented. So there's no possibility of a race condition. After sufficient time, all of these will be processed in some order, but this is irrelevant, and the result will be this. In order to find out that this is happening, we can add a print statement to the reactions. To do that, we can just, for convenience, define a function that emits the counter molecule with a given value and prints that value. Notice here that we are just using Scala code. This is not something magical or special. This is just a Scala function, so it can use other functions like these. This is just ordinary Scala code. As long as you have defined the molecule, or more precisely, a molecule emitter, so this value is called a molecule emitter. This emitter can be called as a function to emit a new molecule. And this call is just an ordinary function call. It can be put into a function and refactored at will. This function could even receive this emitter as one of the arguments, if this is for some reason desired. Molecule emitters are just ordinary local values in your code. And so are reactions. So the result of running this program will be that we will see messages printed. They could be printed in different order, depending on how this is executed. So now let's look at some exercises for you, how to implement various concurrent programs in the chemical machine. So one typical pattern of concurrent programming is producer-consumer. Here is a description. There are several items that can be consumed. Each item carries an integer label. Any process can issue a concurrent request to consume an item, and if an item is available, it should be consumed and the label printed. And if it's not available, then the request should wait until some items become available. It doesn't matter which items we consume. Initially, there should be n items present, labeled by these integers. Your code should attempt to consume 3 items. So as a hint, I can say that clearly the only way to organize this is to put the item values on a molecule or on several molecules and emit them. Also, the request to consume must be a molecule. So you can define a molecule called item carrying integer values and a molecule called consume carrying unit values, and you define a reaction between them that does what is required. Here's the solution. We define an item molecule, a consume molecule, and we define a reaction. This reaction takes an item, takes a consume request. Both of them are input for this reaction. They disappear when the reaction starts, and the value x is printed. Then you emit your initial items. You see the emission is done by calling the molecule emitter as a function. So you can use arbitrary code to do that. And then you emit consume requests. That's it. That's the entire program. It is quite declarative, as you can see. You have written very much just the specification that there is an item, a request to consume, and this is what you do when it is consumed. And this is the initial set of items, and these are the requests. And these things are just definitions that need to be done before you can write this reaction. You need to define the molecules. The next exercise is the batch producer. It's to modify the previous program by having a request that produces a new set of n items, which are labeled like that. As a hint, this request should be modeled by a new molecule. There's no other way in a chemical machine to model any requests, any kind of concurrent action, except by defining a new molecule. Now, since it's just a request with a fixed meaning, we don't need a value for it to be carried. So you define it with unit value, add the appropriate new reactions. Here is a solution. We define a produce molecule, and we add this reaction. The produce molecule emits these item molecules. That's it. That's the entire change that we need. And then we can consume and produce. So since all these requests are concurrent, it doesn't matter in which order we emit them, and they're all non-blocking. So they could be emitted from different concurrently running parallel processes. The next exercise is to make a producer carry a given list of labels, not just the labels from 1 to n, but a list of labels. So that is a trivial change, where the type of the molecule becomes a list of integers, and here we match on that value and emit the item molecules. And here is how we can emit the produce molecule carrying this list. The next example would be to modify the previous program, adding a request to consume 2 items at once. So this can be modeled in a natural way by making a molecule consume 2 that has a reaction that looks like this. This reaction requires as input 2 copies of the molecule item. Of course, they would carry different values in general. And the consume molecule, consume 2 molecule. we are free to define reactions whose input is just one molecule, or 3 molecules, or molecules that have the same kind, or some of them have the same kind and others are not of the same kind. We're free to define any kind of reaction we want. And then we're free to write code that will run when the reaction starts. And the reaction starts as long as all the input molecules are available at the reaction site, which means somebody has emitted those molecules. And here is what we can do. We can emit some produce, some consume, and consume too. So that will print. You can run this and you'll print those messages. Now, an interesting modification would be to have a request that consumes k items, where k is a parameter. Now that is not possible to implement like this, because we cannot write a case expression with an unknown number of terms in the expression. So we have to do it in a different way. And here's how. We consume k with the parameter k, and if that parameter is positive, then we can consume one item and emit a request to consume k-1 further items. So that molecule will be emitted, and if we have more items present at the reaction site, then they will again react with the consume k molecule. This reaction will be run again until either we come to 0, and then nothing will be emitted. So this is an if without an else. And that doesn't do anything when k is 0. Or there are no more item molecules present at the reaction site, and then the consume request will still wait, perhaps, for more items to be produced. So that's how it would work. Now, certainly it would be interesting to have a program that consumes k items atomically. So it either consumes all of them or it consumes none of them. But such a program would be less reliable. Because imagine that items are produced by a number of concurrent processes running in parallel, and we don't know at what time they're produced. So consume 3 at once. It could fail if there aren't 3 items right this moment, but just a moment later there might be some more items emitted. So how do we know that we have failed? It is unreliable. It will sometimes fail and sometimes succeed in this operation. So to make it more reliable, we could implement a timeout. And that would, of course, be possible, but it would be more complicated. So it would consume 3 if they're available before a timeout expires. And if it expires, then it won't consume any. I will not show how this can be implemented right now, but this can be done. However, it's not very reliable because we cannot know when the items are emitted. They're emitted by asynchronous requests, non-blocking requests from processes running in parallel. And we have no control over when they're emitted. And so an operation that demands that all of them are present will often fail with no good reason. So that's probably not a good strategy for a concurrent program. Now, this is an example when we do this. We atomically consume 2 molecules. So this is probably marginally useful, but with a large number of molecules, certainly not very useful. Now, sometimes you make mistakes when writing concurrent programs in the chemical machine. Certainly there is much less code to write, so there are many fewer mistakes that you could possibly make. However, you still do make mistakes. A typical mistake that one makes is to forget to emit a molecule. Imagine that we forget to emit the produce. We emit the consume, but we never emit produce. So then, and also we never emit any item by itself. So then no reaction will ever be able to start because they're all waiting for item and consume, or item and consume K, or produce, and none of them are present. And so the chemical machine will do nothing. It will wait and say nothing. So in this kind of situation, it's useful to debug this, what's happening. And there are many ways of debugging that are supported by the Chymyst library. One of them is by logging the current state of the reaction site, which is called the soup, or the currently this is this log soup method. It's called on a molecule emitter. It prints something like this. It tells you what is the reaction site that this molecule belongs to, and this is the very short designation of that reaction site. So this is the two reactions that we defined here, say, counter and decker, counter and inker. So that's the very short designation of the reaction site. And then it tells you that currently this reaction site has the counter molecule with value 98. So hopefully this will help you to understand why nothing is happening, or whether your program is correctly designed. A short comment about molecule names. Each molecule has a name in the chemical machine, in the Chymyst library. But these names are only used for debugging. So when you do a log soup, then you see these names. But these names are just to help you debug. They do not actually affect anything in the execution. So when you use this syntax to define molecules, the lowercase m is a macro that automatically fills in the name based on the name of the variable that you are using. And that's quite convenient in most cases. But if you need to assign a name yourself, then you can use the longer syntax, which explicitly creates a new value of the class m, the uppercase m. And that class constructor has an argument that you can specify, giving a name. So this declaration is completely equivalent to the shorter one, because the name is the same as the name of the variable. But you can specify an arbitrary name here, and then this name will be used when debugging. Otherwise, everything you define is not based on strings, it's actually values. So this value is the same as this one. These are local values. They can be renamed at will. It doesn't change the logic of the concurrent application. So let's have a brief overview of errors that one can make when first starting to use the chemical machine. The first error that I also sometimes make is to start emitting molecules before defining a reaction site for them. I say that molecules are bound to a reaction site when you define a reaction that consumes this molecule and put that reaction on a reaction site. Only then there is a data structure that can hold the molecules you emit. So before defining that, it's an error to emit molecules. And you can check if molecules are bound or not yet bound. So after you do this, the molecule will be bound and you can emit it. Another error that one could make is to try redefining the chemistry, so to speak. Change the reactions. So a typical error is to first define this reaction that consumes X and A. So X and A are some molecules. And then define another reaction that consumes X and B in a different reaction site. And that's not allowed. Reactions that consume X must be able to automatically find the value of X. And they have to look at a specific reaction site, namely here, and the one that contains them. They cannot look at some other reaction site. And so, for this reason, this is an error. The right way of declaring such a program is to put both of these reactions at the same reaction site. And this is necessary whenever you have reactions that consume the same molecule. These reactions contend on this molecule, they compete for it, and the only way to do this correctly is to put these two reactions at the same reaction site. When the molecule X is emitted, it will go to this reaction site, and then these two reactions will be able to decide which one of them could start, maybe. Reactions that use a molecule as output, they can be defined in a different reaction site. That's not a problem. For example, this show molecule is defined at some reaction site, and this start molecule is defined bound to this reaction site. So when you emit a start molecule, this reaction will run. It will emit the show molecule. The show molecule will go to that reaction site and start this reaction. So that's fine. You're emitting a molecule that goes to a different reaction site. That's not a problem. There's no question of where a molecule should go when emitted. There must be only one reaction site to which each molecule should go when emitted. And all reactions that consume this molecule must be defined at that reaction site. So this is the way that the chemical machine limits you from being able to define new reactions later. And a result of this is that reactions are immutable. The logic of what will start, possibly, when some molecule is emitted, this logic is immutable. Once you create a reaction site with some reaction, you cannot later add more possibilities to consume the same molecule. And that's important for encapsulation. Molecules are immutable, reactions are immutable, and reaction sites are immutable once defined. Another important idea that the chemical machine naturally follows is indeterminism. There is no order in which reactions must proceed. The order is determined by what molecules are available. But if more than one reaction could start, then we don't know which one would start. Imagine that a reaction site has counter molecule, increment molecule, and decrement molecule at the same time. So then either these two could react and decrement the counter, or these two could react and increment the counter. The runtime of the chemical machine will make that decision in an unspecified way. You have no control over that decision. You could not say that you want to prefer this molecule, or that you want to prefer this reaction. It's not possible to do that, to say that. And here's what happens. You imagine you have a counter molecule and a bunch of increment molecules. One of them will react. You get this. And now you have this situation where you have a counter molecule. All these previous molecules are still around. And then this new molecule will react with one of those. Or maybe with this one, but one of them only at one time. Then you would have n plus 2. And then the same thing will repeat. So the runtime of the chemical machine will choose which molecule to react with, only one at a time, because only one copy of the counter molecule is available. If you had emitted 2 counter molecules at the same time, and more than 1 increment molecules, then the chemical machine could have run several of these reactions in parallel. But if you only emit 1, then it cannot do that. And so in this way, the programmer controls the logic of the concurrent application, only in the way of limiting what data is available for reactions. This is a very important idea. We cannot assign any priorities to reactions or to molecules. The only way we can control the concurrent logic is by limiting what molecules will be available at the reaction site. And we don't know when they will be available. There are no guarantees as to when exactly something will happen. And this is actually a very important feature of the chemical machine. Because if you have a concurrent system where processes run in parallel and produce results at unpredictable times, then your logic of what process next to start cannot depend on the sequence in which some results are obtained. The chemical machine explicitly prohibits you from assigning priorities or orderings on reactions, and therefore you must squarely face the problem of organizing the computation such that the results are independent of the possible indeterminism. If we added the feature of priorities to the chemical machine, that would actually be counterproductive. It would give us an illusion of control over the order of reactions without actually giving us reliable control. Here is why. Suppose we want to implement a program that receives a bunch of numbers and computes their sum, and then reports, say, prints the final sum value. Our intention is that there will be a certain number of data molecules that some other process will deliver to us by emitting them. And when all of them arrive, then we print the sum. So let's try to implement this in a simple way. And we define the data molecule, which will carry the value. We define the sum molecule, which will accumulate the sum. Whenever a data molecule arrives, we consume a data molecule, a sum molecule, and we emit a new sum molecule with updated value. And then we think, when there are no more data molecules, then we run this reaction that just takes the sum molecule and prints the value on it. So what we want is that this reaction runs as long as any data molecules are available. And after that, when they're all consumed, we're done, this reaction will run. This program, however, is unreliable, because the chemical machine does not allow us to say that the first reaction has priority over the second one. The order in which we declare the reactions in the reaction site is completely unimportant. So the chemical machine is free to run this reaction as long as any sum molecule is present. So if we now emit molecules like this, it could be, depending on runtime conditions, that the chemical machine will immediately start this reaction and print 0. And then it will do nothing else. Or it could be that it actually first runs this reaction a few times and prints some other number. So this program will be unreliable. And the fact that this program is unreliable is much more apparent when you write the program using the chemical machine. It is obvious that you are not actually controlling which reaction will run. The sum reaction takes just one molecule as input, so it can always be started whenever you have a sum molecule. So obviously you are not in control here. So actually, the Chymyst library knows to check such things, and it will give you an error when you even if you just try to declare this reaction site, it tells you that there's an error in that there's an unavoidable indeterminism in the reactions. One reaction can be run, and another reaction can be run as well, undeterministically, when you have the two molecules. The Chymyst library assumes that this situation is not what you want. There's an error. And in fact, if data molecules arrive in unpredictable times, there's no good solution here. Even if you were able to say that this reaction has a lower priority, then the chemical machine will determine that there are no more data molecules, but how does it know that maybe some parallel process is running right this second and is about to emit one more data molecule? It doesn't know that. There's no reliable way to determine that a data molecule is absent right this second, because what is right this second? You may wait 1 millisecond and some process already emits some more data molecules. It's very unreliable, and the chemical machine makes it apparent, much more easily apparent than other concurrency approaches and methods. So the right way of doing this is to keep track of how many data molecules have been already consumed. So we need to know the number of those molecules that we expect. We put this number onto the sum molecule together with its accumulated sum. So we have now a sum molecule that carries a tuple of two integers. That's how we could define it very easily. And then we continue summing up only when there's some remaining data items that we expect. Now, notice here we're using standard Scala, a case expression with a guard condition. So this is standard in Scala. This reaction will start only when these molecules are present and when the value on this molecule satisfies the guard condition. Otherwise, this reaction will not start. This is how the chemical machine works. And finally, this reaction will start only when there is a sum molecule that doesn't expect any more data molecules to arrive. So it will start only when this pattern match succeeds on the molecule value. So in this way, we very easily control when we print the result and when we still keep waiting. So this is now reliable. You see, there's not much more code that needs to be written, but the chemical machine forces you to consider these things. Another way of doing the same thing with just one reaction is to have a more complicated reaction code where we already print the sum when the remaining is 1. Because if the remaining is 1, we have this 1 right here, then we don't need to emit 0 and then start a second reaction with 0. We can just put that code right in here. That's up to us. But now we have a more complicated branching code inside of a reaction. This could be okay, but this code is perhaps easier to understand. It's up to us. So what have we seen so far? In the chemical machine, we write programs by first defining the molecules and their value types, then defining the reactions that consume these molecules, together with reaction sites that these reactions belong to. And then we emit some initial molecules. So this is the typical layout of a chemical program that we have seen so far. Declarations of molecules, define a reaction site with this reaction, emit initial molecules. And after we emit initial molecules, we simply wait. We don't have to do anything else. No more code. So we just wait. The chemical machine runs all the reactions and does whatever we want. So in other words, the task of the programmer is to figure out what molecules to define, what reactions to define, in which reaction sites, and which initial molecules to emit. And that's it. The programmer is free to define one or more reaction sites, or reactions, or molecules at any time. Any place in the code we can emit molecules, refactor this in any way as is convenient. I summarized some more details here, but let me skip this. You can read this chapter in more detail later. And here is an interesting example of a so-called dining philosophers problem, which is solved very elegantly by the chemical machine method. The problem is that there are 5 philosophers. They're sitting at a table, and there's a fork between each of 2 philosophers that are next to each other. And they do the following. Each of them, at random times, becomes hungry and wants to eat. And to eat, the philosopher needs 2 forks. So the philosopher takes the 2 forks next to that philosopher and uses them for eating. And while that philosopher eats, therefore, none of the neighbors can eat because the fork is taken. When the philosopher, again, after a random time, stops eating, the philosopher puts the forks back on the table. So the problem is to simulate this behavior and to decide who gets to eat and when, so that they don't wait too much for each other. I will show only the simplest solution. There are several solutions possible of varying degree of complexity. The simplest solution is to model each philosopher by a molecule, and actually by 2 different molecules. One showing that the philosopher is eating, and another one that the philosopher is not eating, or as we say, thinking. We don't really know if the philosopher is thinking, but we know that the philosopher is not eating at that time. Let's call that philosopher a thinking one. So we have 5 molecules for each philosopher that is thinking, and 5 molecules for philosophers that are eating. Each fork will be a molecule as well, and the presence of the molecule would mean that the fork is available. So then let's define a function that sleeps a random time and prints a message. So that's easy. Then we define these molecules. 5 philosophers who are hungry, 5 philosophers who are thinking, and 5 forks. Now, hungry is not actually the same as eating. Hungry means the philosopher is about to eat, is looking for forks. And then we write the code. So the reactions that consume these molecules are as follows. A thinking philosopher is consumed. So this philosopher stops thinking, waits an arbitrary random time, and becomes hungry. A hungry philosopher takes 2 forks next to both sides. Then all these molecules disappear while there's a waiting time. That represents eating. And then the 2 forks are emitted back, and a thinking philosopher molecule is emitted back. So in this way, we directly represent the requirements of this problem. And that's the entire code. After this, we just need to emit the initial molecules, the 5 initially thinking philosophers, and the 5 forks that are initially present on the table. And that's it. That's the entire code. It's completely declarative. It just expresses the requirements of the problem, that the thinking philosopher waits a random time and becomes hungry. A hungry philosopher takes 2 forks, waits a random time while eating, and becomes again a thinking philosopher and returns the 2 forks. And so for each philosopher. And this code can be run using the Chymyst library. And the print output might look something like this. So they're all eating and thinking in some random order. So this solution is the simplest one. It is fully declarative. There's no code here except a declaration of the rules of the problem. And this is already executable code. There are 2 improvements that you can make to this code. One would be to implement an arbitrary number of philosophers. And another is to implement fairness, so that the philosopher starts eating only when none of the neighbors has been waiting longer for the forks. So that is a more difficult problem, but it is still implementable very easily in very concise code using the chemical machine. In my experience, the code for the chemical machine is usually much shorter than the code for other concurrency methods. The site Rosetta Code has examples of implementing the dining philosophers problem in different programming languages. So here is, for example, a solution in C++. And here's a solution in Go. You see, it's even in a language like Go that is supposedly very suitable for concurrent programming, the solution is quite complicated. It is not very declarative. It's a dominant hand, other hand, there's a right, there are all these things that you have to write. It's not very long, it's certainly shorter than C++, but cannot compare it with the solution in the chemical machine. So one implementation of the chemical machine is for the OCaml language, which is called JOCaml. And the solution in JOCaml looks like this. This is the entire code. The Joe-Camel syntax is similar to the syntax of Chymyst, but Scala requires some more boilerplate. In Joe-Camel, you don't need to define the molecule names separately. They use the ampersand symbol instead of plus, otherwise it's basically the same. If you look at a language like Oz, it also has special provisions for concurrency, but still, the program is quite complicated and it's hard to understand what it does. So we look at the solution in Prolog. It's not very short. It's kind of complicated as well. The solution in Rust. That is short, certainly, much shorter than Prolog. Using mutex. This is just to illustrate that Python, that the chemical machine gives you a possibility to write code that is very concise, very declarative, and easy to understand. Now this is certainly not easy to understand. Break, then release. Do I acquire this first and this then, or in the other order? Not clear. Not declarative. This is declarative. There is nothing that is unclear, and the program is obviously correct. So this concludes the tutorial. I'm encouraging you to look at this documentation in more detail. This is the first chapter of the documentation book for the Chymyst library. The documentation contains many more examples worked out in detail of how to design programs, how to derive programs logically from their specifications. And usually the programs are very short. And usually it's obvious what molecules you need and what reactions you need once you start thinking about them and try to imagine the chemical reactions between molecules.